Good day everyone, I am Jahzel Belascuain and together with Ms. Ronawel Luyong and Ms. Imee Praile, we will be presenting about magmatic concentration deposits. So what are magmatic concentration deposits? These are mineral deposits that form when certain elements within cooling magma become concentrated and crystallized. These deposits typically occur in large, intrusive igneous bodies and are characterized by the presence of heavy, dense minerals such as sulfides and oxides. During the crystallization process, these metals tend to sink at the bottom of the magma chamber, leading to the formation of layered accumulation. Magmatic deposits are often associated with mafic to ultramafic rock types, which are low in silica but rich in iron and magnesium. Such deposits are economically significant as they serve as major sources for valuable metals like nickel, chromium, platinum, and copper, which are widely used in various industries, including electronics, aerospace, and manufacturing. The study and exploration of these deposits are crucial for resource extraction as they provide essential raw materials for modern technology and infrastructure. The information presented in this slide is based on United States Geological Survey or USGS, specifically from Zintec 2012. Another definition is from Cambridge University, specifically Ridley 2013. Magmatic concentration deposits, also known as magmatic ore deposits or orthomagmatic ore deposits, are mineral accumulation found within igneous rocks or along their contacts. These deposits form when ore mineral crystallize directly from the molten state or are transported within the magma before settling and solidifying. They are typically associated with mafic and ultramafic igneous rock, which provide favorable conditions for metal concentration. In contrast, some ore deposits, particularly those forming in and around igneous rock units, results from hydrothermal processes where mineral-rich aqueous solution or hydrothermal fluid precipitate valuable metals, forming hydrothermal ore deposits. This distinction is significant in mineral exploration as magmatic deposits typically host dense heavy minerals like sulfides and oxide, while hydrothermal deposits result in fluid-driven chemical reactions. Based on the two definitions previously, there are two formations of magmatic deposits, which are simple crystallization and concentration by differentiation of intrusive igneous rocks. The mineralogy of magmatic deposits are largely influenced by the presence of volatile elements such as sulfur, fluorine, and fluorine, which play a crucial role in the formation and differentiation of minerals. These elements contribute to the crystallization of minerals like apatite, magnetite, and fluorite, which are commonly associated with magmatic processes. During the cooling and solidification of magma, a variety of minerals may form, including feldspar, mica, and quartz, which are characteristic of igneous rock formation. Many of these minerals hold significant economic value, particularly those rich in metals or rare elements. Understanding the mineral composition of magmatic deposit is essential for mineral exploration and economic geology. The mineralogical composition of magmatic deposits consists of various dominant minerals, primarily categorized into oxides, sulfides, and platinum group elements or PGE. Oxide minerals such as chromite, magnetite, ilmenite are commonly associated with igneous rock formation and play a significant role in the differentiation and crystallization process of magma. In addition to oxides, sulfide minerals such as pentlandite, chalcopyrite, and pyrrhotite are commonly found in magmatic deposits. These sulfides are crucial ore minerals for nickel, copper, and iron, making them highly significant in mining and metallurgy. Magmatic deposits can also host platinum group elements including platinum, palladium, and rhodium. These elements are typically found in association with sulfide minerals and are highly valuable due to their industrial application, particularly in the automotive, electronic, and jewelry industry. PGE are rare and primarily mined from layered mafic ultramafic intrusions. The mineralogical composition of magmatic deposits are closely linked to the types of host rock in which these minerals are formed. These deposits are typically found in mafic and ultramafic igneous rocks such as gabbro and peridotite. These types of rocks are characterized by their low silica content and high concentration of iron and magnesium and other compatible elements. Mafic and ultramafic rocks originate from the cooling and crystallization of magma rich in these elements. Due to their geochemical composition, these rocks plays a significant role in controlling the distribution of metallic ore deposits. The study of host rock also provides insight into the geological history and magmatic processes that lead to the formation of mineral-rich deposits. For texture and structure, we have layered intrusion, cumulate texture, and ophitic texture. Layered intrusions are distinctive geological features formed through fractional crystallization and crystal settling in a cooling magma chamber. This structure develop as mineral crystallize at different temperature and densities, causing them to separate into layers over time. This process results in visible stratification, as seen in the picture. It is the gabbro from the Gills Complex, South Australia, which showcase uniform layering. Next is cumulus texture. It is formed by the accumulation of early formed crystal at the base of magma chamber, a process known as crystal settling. This occurs because different minerals crystallize at varying temperature, and as heavier minerals form first, they sink due to gravity, creating distinct layers. Over time, this results in size grading layering, as seen in the picture, the Duke Island intrusion in Alaska, where cumulus mineral exhibit a smooth variation in grain size. Ophitic texture is a variant of poikilotic texture, where randomly oriented plagioclase lath are enclosed by larger pyroxene or olivine crystals. The image provided is a cross-polarized light micrograph magnified ×2, showing augite crystal with embedded plagioclase inclusion. This texture formed due to slow cooling magma, allowing the larger ferromagnesian minerals to grow around the already crystallized plagioclase. The interlocking nature of the lath are often forming sharp angles, providing clues about the cooling history and crystallization sequence of the rock. The presence of ophilic texture in a rock sample suggests it originates from subsurface magma chamber, as it requires moderate cooling rates, faster than plutonic rocks but slower than volcanic lavas. For this part, we have classification of magmatic deposits. Under this are early magmatic deposits, late magmatic deposits, and immiscible deposits. First is the early magmatic deposits. Early magmatic minerals have crystallized before the formation of the rock-forming constituent of the enclosing rock. It refers to the mineral concentration that formed before the complete crystallization of host rocks, meaning that the mineral crystallized early in the magmatic process. These deposits originate from molten rocks that cool and solidify, often deep within the Earth's crust. The early crystallization of certain minerals allowed the enrichment of economically valuable elements such as chromium, nickel, platinum, and magnetite within igneous intrusions. The type of processes of early magmatic deposit outline three main processes: dissemination, segregation, and injection. First is the dissemination. It occurs when minerals crystallize from deep-seated magma and are distributed throughout the host rock. This process results in the formation of diamond-bearing kimberlite pipes and corundum deposits, which are both significant sources of gemstone and industrial minerals. Next is segregation, or layered type. It happens when minerals separate due to gravitational settling within a magma chamber. These occur as the magma cools and differentiate, causing denser minerals to sink and accumulate in layers. This process led to the formation of layered chromite deposits and platinum group elements, which are crucial for various industrial and technological applications, including stainless steel and catalytic converters. And lastly is the injection. It involves the transport of mineralized magmatic fluid into surrounding rock formation due to the tectonic activity. This movement allows the concentration of minerals such as magnetite, and some chromite deposits, which are essential for steel production and other metallurgical processes. Next classification of magmatic deposits is late magmatic deposits. These are formed during final stages of magmatic cooling and solidification. As magma cools, the more mobile residual magmas remain, allowing ore minerals to crystallize later than the primary rock-forming minerals. This late-stage crystallization leads to the concentration of valuable minerals in specific zones within the igneous bodies. Late magmatic deposits result from two key processes, segregation and injection. Segregation occurs when ore mineral crystallize from the residual magma and accumulate in specific zones, often within mafic igneous rock. This process leads to the formation of iron and titanium ore bodies, which are valuable for industrial applications. The accumulation of these minerals happen due to density differences, causing heavier minerals to settle and concentrate in layers. Injection, on the other hand, happens when the residual magma, still mobile, is forced into fracture and surrounding rock formation. This movement allows for the formation of pegmatites and carbonates, which are known to contain rare elements such as lithium, niobium, and rare earth minerals. These deposits are significant in the mining industry due to their economic value. And the last classification of magmatic deposit is immiscible deposits. It forms when magma undergoes physical separation into two distinct liquid phases that do not mix. One phase is typically sulfur-rich while other is silicate-rich. This immiscibility results in the formation of metal-rich ore bodies within the cooling magma. The immiscible melts may form as irregular shape segregation, where dense sulfide liquids accumulate in specific area, or they may be injected as dikes into pre-existing crystallized rock formation. Similar to late magmatic deposits, immiscible deposits also develop through segregation and injection processes. First is the segregation processes. During the late stage of magmatic crystallization, a drop in temperature causes metal sulfides such as iron, nickel, and copper to separate as immiscible liquid droplets within the magma. These droplets remain in liquid state until the surrounding silicate minerals fully crystallize. Over time, the immiscible liquid sulfide droplets accumulate at the base of the magma chamber, where they eventually solidify and form sulfide segregation. These segregations are economically important as they are rich in nickel sulfides, copper sulfides, and platinum group minerals. Next is the injection process. If tectonic disturbance affect the immiscible fraction of magma before it solidifies, the sulfide liquid can migrate towards the area of lower pressure through fracture or weak zone in the surrounding rocks. Once it reaches a stable environment, it consolidates and crystallizes, forming injection-type immiscible deposits. These deposits primarily consist of sulfide minerals and may be hosted in dikes or fracture rather than settling at the base of the magma chamber. The image presents a periodic table highlighting elements associated with magmatic ore deposits, categorized based on their geochemical behavior. The classification follows Mungal 2013, distinguishing three main groups: incompatible lithophile elements, the light gray; chalcopile elements, medium gray; and compatible lithophile elements, dark gray. Incompatible lithophile elements do not readily fit into the crystal lattices of solidifying minerals and tend to remain in the residual melt, contributing to late-stage magmatic processes. Chalcophile elements have a strong affinity for sulfur and tends to form sulfide minerals. These elements often concentrate in layered mafic intrusion, where they crystallize with sulfide-rich magma. Next is the compatible lithophile elements. Readily incorporate into early crystallizing minerals, becoming concentrated in solid phase of cooling magma. These elements are essential for forming oxide-rich deposits such as magnetite and ilmenite ores. Next, we have the notable magmatic deposits. Bushveld Igneous Complex is one of the world's most significant layered mafic intrusion located north of Pretoria, South Africa. This layered mafic intrusion hosts a diverse array of ore deposit types. which is one of the world's largest sources of platinum and chromium. The deposit is about 2 billion years old and covers an area of about 66,000 square kilometers, making it one of the most extensive igneous bodies on Earth. The Bushveld Igneous Complex plays a crucial role in the global supply of platinum, which are extensively used in catalytic converters for automobiles, jewelry, and electronic components, while chromium from the complex is a vital component in stainless steel production. Sudbury Basin, located in Ontario, Canada, is one of the largest impact structures on Earth and contains a massive magmatic deposits that is rich in nickel, copper, and platinum group metals. The deposit was formed by a meteor impact about 1.8 billion years ago, creating a large crater that later underwent extensive geological transformation. The impact led to the melting and mixing of Earth's crustal material, which facilitated the formation of a magmatic sulfide deposits. And the last example is the Palabora Copper Open Pit Mine, located in Palabora, Limpopo Province in South Africa. It is one of the world's largest sources of copper and contains significant amount of gold and silver. It is located in a large carbonate complex that was formed about 2 billion years ago. The mine was originally developed as an open pit operation, but as surface resources became depleted, underground mining methods were introduced to continue extraction. The deposit is particularly notable for its high copper concentration and the presence of valuable byproducts such as vermiculite, zirconium, and phosphate minerals, which have important industrial application. And those three are some of the most notable magmatic deposits. And for the next part of the presentation, we have Miss Imee Praile.
Magmatic concentration deposits has 5 types. First is the magmatic segregation deposits, second is the magmatic sulfide deposits, third is the pegmatites, fourth is the carbonatites, and lastly is the skarn deposits. The first type is the magmatic segregation deposit. This was formed as magma cools and crystallizes, concentrating minerals in specific layers. This is commonly found in layered igneous intrusions such as Bushveld Complex in South Africa and the Great Dyke in Zimbabwe. Magmatic segregation deposits was formed through the process involves gravity settling and fractional crystallization. In gravity settling, the denser minerals sink to the bottom of the magma chamber, while on the fractional crystallization, minerals crystallize at different temperatures, concentrating specific elements in layers. The typical example minerals formed through magmatic segregation include chromatite, magnetite, and ilmenite. Chromatite is the main source of chromium. It is found in ultramafic rocks like peridotites, formed through magmatic crystallization. Next is the magnetite. It is a major iron ore and a source of vanadium in titaniferous deposits. It is a perimagnetic iron oxide that occurs in igneous rocks, skarns, and banded iron formation that often forming through magmatic segregation or metasomatic alteration of limestone. The last type of minerals formed in magmatic segregation deposits is the ilmenite. It is a principal titanium ore, typically forms in mafic and ultramafic igneous rocks as part of layered intrusion or in placer deposits derived from weathering and erosion of primary sources. The next type is the magmatic sulfide deposits that form when sulfide liquids separate from mafic or ultramafic magmas in active magmatic system. These deposits come from mantle-derived magmas like picritic or tholeiitic basalt. It has become rich in sulfur through the process of crustal assimilation, magma mixing, and fractional crystallization. As a result, sulfur accumulates, lead to the formation of magmatic sulfide deposits. Platinoids. It is one of the minerals formed in magmatic sulfide deposit. It contains platinum group elements or PGEs like platinum, palladium, and rhodium. This Pg is concentrated in sulfide liquids during the crystallization of mafic and ultramafic magmas due to their strong affinity for sulfides. The major deposits include the Bushveld complex in South Africa and the Norilsk Talca region in Russia. Next is the nickel. It is found in association with copper and cobalt in magmatic sulfide deposit. It is formed when nickel-rich sulfide droplets separate from silicate magmas and settle in magma chambers. They are typically located in the areas with significant ultramafic rock formations. Last is the copper. It is commonly extracted from both magmatic and sedimentary environments. It is often occurs alongside nickel and PGEs within sulfide minerals. Copper deposits can also form through hydrothermal processes or as a byproduct of other mining activities. The third types of the magmatic concentration deposits is the pegmatites. It is a coarse-grained igneous rocks that form from the late stage crystallization of granitic magmas. They are typically appear as dikes, sills, or irregular shapes near granitic plutons or in areas with high-grade metamorphism. The common location for pegmatites include the fracture zones, batholiths, and regions where continental plates collide and the crust thickens. The key features of pegmatites is their rare element enrichment, significant mining areas, and their large crystals. Niobium. It is one of the minerals formed in pegmatites. It is found in rare metal pegmatites enriched in niobium tantalum minerals. It occurs in carbonatites and alkaline igneous rocks as minerals like pyrochlore and columbite tantalite. These deposits are critical for producing high-strength steel alloys and superconducting materials. Next is the tin. These deposits are often linked to highly evolved granites and especially associated with tungsten and lithium mineralization. This is formed in hydrothermal veins, gracens, and pegmatites associated with granitic intrusions. The major tin-producing regions include the Southeast Asia and South America. Last is the beryllium. It occurs as beryl, which is commonly associated with quartz, feldspar, and muscovite. These pegmatites are enriched in rare elements and are often zoned with beryl forming in the inner zones. These non-pegmatitic deposits, such as hydrothermal veins and gracens, are also hosts of beryllium minerals, making it a critical resource for aerospace and electronics industry. The next type of magmatic concentration deposits are carbonatites. It is formed from carbonate-rich magmas that come from the Earth's mantle. This can happen through partial melting of the carbonate-rich rocks, liquid immiscibility, or when different liquids don't mix, and extreme fractional crystallization of alkaline silicate magmas. They are found in areas with tectonic activity like rift zones and intraplate regions where the magmas rise to the crust. The carbonatite associated deposits can be classified as magmatic or metasomatic types. Magmatic type are classified into four types. This is the calciocarbonatites, magnesiocarbonatites, ferrocarbonatites, and natrocarbonatites. Carbonatites are classified based on their mineral composition and geological formation processes. The first type is the calciocarbonatites that is made mostly of calcite found in places like Palabora complex in South Africa. Next is the magnesiocarbonites that contain mainly dolomite or magnesite, less common and often formed deep in the Earth's mantle. Next is the ferrocarbonatites that is rich in iron carbonites like siderite, often linked to valuable rare earth elements. And lastly, the natrocarbonatites that contains lot of sodium-rich carbonites and very rare and found in only active carbonatite volcano which is the O1 Donyo Lingay volcano in Tanzania. Metasomatic types. It is a process where surrounding rocks change when they come into contact with fluids and melts rich in carbonates. This is usually happens when carbonatite melts rise and interact with the Earth's mantle or crust. It causes changes in the minerals and chemistry of the nearby rocks. Skarn deposits. It is the last type of magmatic concentration deposits that form when hot, metal-rich fluids from igneous rocks interact with carbonate rocks like limestone, creating silicate-rich metamorphic rocks called skarn. These deposits often contain valuable metals like copper, gold, silver, zinc, and tungsten. This is important and provide insights into geological processes. The formation of skarn deposits involves several key stages. First is the intrusion, second is the contact metamorphism, third is the fluid release, fourth is the metasomatism, fifth is the mineral formation, and lastly is the ore deposition. First stage is the intrusion, where a body of magma, often granitic, pushes into the carbonate-rich sedimentary rocks. Second is the contact metamorphism, when the heat from the magma causes the surrounding rocks to undergo initial metamorphism. It leads to the formation of hornspels or skarnorms. The third stage is the fluid release. As the magma cools, it releases hot mineral-rich fluids. And the stage 4 is the metasomatism, which is when the fluids react with the surrounding carbonate rocks, resulting in the chemical changes and mineral replacement. And the fifth stage is the mineral formation. It is the interaction leads to the creation of calc-silicate minerals, mainly garnet or pyroxene. And the last is the ore deposition. It is the valuable ore minerals can precipitate during this process, creating economically significant skarn deposits. There are five main types of skarn deposits. First is the calc-silicate skarns, second is the magnetite skarns, third is the chloride skarns, fourth is the tungsten skarns, and lastly is the gold skarns. The calc-silicate skarns is associated with calc-alkalines, igneous rocks such as diorite, quartz, diorite, and granodiorite. It does typically contain minerals such as garnet, pyroxene, and wollastonite. Second is the magnetite skarns. This is associated with magnetite-rich rocks such as mafic or ultramafic intrusions. This is typically characterized by the presence of magnetite and pyroxene as well as other minerals such as garnet and amphibole. Third is the chloride skarns that is associated with rocks that is rich in chloride such as serpentinized ultramafic rocks. They typically contain minerals such as garnet, epidote, and antinolite. Next is the tungsten skarns. These are skarns that are enriched in tungsten and typically associated with granitic rocks. They are characterized by the presence of minerals such as scheelite, wolframite, and molybdenite. And lastly is the gold skarns. Skarns that are associated with gold mineralization and are typically associated with granitic rocks. They are characterized by the presence of minerals such as pyrrhotite, pyrite, and arsenopyrite.
Next is ore-genesis. What is ore-genesis? The process where valuable minerals concentrate within a magma chamber during its cooling and crystallization that leads to the formation of ore deposits through mechanisms like crystal settling, liquid immiscibility, or the sulfide melt separation and fractional crystallization, primarily concentrating elements like nickel, copper, platinum group metals, chromium, and iron in the form of oxides and sulfides at the base of the magma chamber. These processes occur over geological time and involve the concentration of metals from the Earth's crust through various geological, chemical, and physical mechanisms. Magmatic processes are the igneous ore-genesis, hydrothermal processes are the hot water activity, sedimentary processes, metamorphic processes, and weathering and supergene enrichment are the major processes of ore-genesis. First is the magmatic processes or the igneous ore-genesis. Here, metals undergo crystallization from cooling magma and settle into layers or veins just like in the picture. Commonly forms nickel, platinum, chromite, and magnetite deposits. Example of this process is Bushveld Complex in South Africa, the major platinum deposit. It is one of the world's largest and most important platinum group element deposits. It is a massive layer mafic ultramafic intrusion that formed about 2 billion years ago. Second is the hydrothermal processes or hot water activity. Hot mineral-rich fluids move through cracks and fractures, depositing metals as they cool that leads to the formation of gold, silver, copper, lead, zinc, and tin deposits. Example of this process is porphyry copper deposits, which is found in Chile, USA, and Indonesia. Their large size and widespread distribution make them crucial for global copper supply, supporting industries and infrastructure worldwide. Next is the sedimentary processes. Metals accumulate in sedimentary layers through weathering, erosion, and chemical precipitation, and metals accumulate in sedimentary layers produces iron ore, manganese, and evaporite minerals like salt and gypsum. Also, lead to the formation, transportation, deposition, and lithification of sediments. An example of this process is banded iron formation or the BIFs in Australia and Brazil. These are ancient sedimentary iron-rich rock deposits that formed around 2.5 to 3.8 billion years ago. Metamorphic processes. Heat and pressure alter pre-existing rocks, releasing and concentrating valuable minerals, leading to the creation of graphite, talc, and some gold deposits. This involves the transformation of existing rocks such as igneous, sedimentary, or even older metamorphic rocks into new metamorphic rocks due to the heat, pressure, and chemically active fluid. Example is gold in greenstone belts in Canada and Australia. Lastly is weathering and supergene enrichment. Rainwater and surface processes dissolve and redeposit metals, enriching existing deposits. This enhances copper, aluminum or bauxite, and iron ore deposits. These processes involve the breakdown of rocks and minerals at or near Earth's surface that leads to the transportation and redeposition of valuable metals in enriched forms. Example is bauxite deposits in Jamaica, Guinea, and Australia. Ore genesis and magmatic concentration deposits. Magmatic concentration deposits form when valuable minerals crystallize from cooling magma and become concentrated within igneous rocks and through the crystallization and differentiation of magma within the Earth's crust. These deposits are associated with igneous processes and are a major source of metals like chromium, nickel, platinum, titanium, and iron. Processes involved in magmatic ore genesis are fractional crystallization, gravity settling, immiscibility or the liquid separation, and magmatic injection and differentiation. In fractional crystallization, as magma cools, minerals crystallize at different temperatures and heavy metal-rich minerals settle at the bottom of a magma chamber that leads to the formation of layered deposits. Example is Bushveld complex in South Africa and the platinum and chromite deposits. Next is gravity settling. It is a process in which heavy minerals separate from a cooling magma due to their higher density. This occurs in magmatic intrusions where minerals crystallize and sink to the bottom of the magma chamber, forming layered mineral deposits. Example is Stillwater complex in USA that has platinum and palladium deposits. Immiscibility or the liquid separation. This refers to the process where two or more liquids in magma do not mix, that cause them to separate into distinct phases. In ore formation, this occurs when a metal-rich sulfide liquid separates from the silicate magma that leads to the concentration of valuable metals like nickel, copper, and platinum group elements. Example is Sudbury Basin in Canada that has nickel and copper deposits. Lastly is the magmatic injection and differentiation. When we say magmatic injection, this occurs when new pulses of magma enter an existing magma chamber, bringing in fresh material and metals, while magmatic differentiation is the process by which a magma body evolves and separates into different mineral compositions as it cools. Magma can intrude into surrounding rocks, cooling at different rates and forming mineral-rich veins. These deposits are often associated with titanium and vanadium. Example is the Duluth complex in USA that has a copper, nickel, and platinum group elements, or the PGEs. Here are the economic importance of magmatic ore deposits. First, it is essential for modern industries like steel, batteries, and electronics. Second, it is major sources of strategic metals like nickel for electric vehicle battery, platinum for catalytic converters, and lastly, and the third one, is high-grade, large deposits make them prime targets for mining. Structural control or deposits. These are structures, tectonics, and surface weathering play a vital role over geological time as a passage for hydrothermal flow of mineralized fluids, accumulate and concentrate at suitable location, remobilize and reorientate as post-genetic activity. The features related to the mineralization control are deformation, weathering, joints, fractures, faults, breccias, and plate tectonics. These structures create pathways for ore-bearing fluids, control the deposition of minerals, and enhance the economic viability of a deposit. Here are the structural controls. First is the undeformed. These are geological formations that have not experienced significant structural changes such as folding, faulting, or shearing. Most of the residual and placer deposits are undeformed type such as East Coast Bauxite Deposit in India. Second is the joints and fractures. These are natural breaks or cracks in rocks that form due to stress, weathering, and tectonic activity. These structures influence fluid movement, rock stability, and mineralization processes. Third structural control is fault. This is caused by directed compression of the crust, and the fault closure, limbed inflex zone, and axial planes are suitable for mineral localization. In the picture beside it, anticline and syncline is very evident. Anticline is the upwards arcing fold, which is the oldest rocks in the center, while syncline is a downwards bending fold and the youngest rocks in the center. Fourth structural control is faults. These are fracture or break in the Earth's crust where significant movement has occurred due to the tectonic forces. Fifth is shear zone. It is a region of the Earth's crust where rocks have undergone intense deformation due to the shear stress. It represents a zone of high strain where rock layers slide past each other, often forming under ductile or brittle ductile conditions. Sixth is breccia. It is a type of rock composed of angular, broken rock fragments that are cemented together by a fine-grained matrix. The fragments are called clasts and can vary in size and are typically sharp-edged that indicates minimal transport before deposition processes. Lastly is subduction zone. It is a region where one tectonic plate is forced beneath another and sinks into the mantle due to the plate convergence. This process occurs at convergent plate boundaries, typically where oceanic and continental plates meet. The formation of subduction zone is closely associated with multidimensional tectonic activities like shallow and deep focuses earthquakes, melting of mantle, volcanism, rising magma resulting to volcanic arc, plutonic rocks of ophiolite soothes, platinum chromium bearing peridotite, dunite gabbronorite, and the movement of metal bearing hydrothermal solution and metamorphic dewatering. Chemical controls. This refers to the geochemical conditions that influence the precipitation and deposition of minerals from ore-forming fluids, and these controls determine where, when, and how minerals crystallize from solutions that affects the size, composition, and the quality of the ore deposits. Here are the key chemical controls. First is the pH or the acidity versus alkalinity. The acidity or alkalinity of a fluid affects mineral solubility. If the pH level is less than 7, then it is acidic. If it is balanced, it is neutral. And if the pH level is greater than 7, then it is alkaline. Second is the redox or the oxidation-reduction conditions. These refer to the balance between oxidation and reduction reactions in a system. When we say oxidation, it is a process where a substance loses electrons or the increase in oxidation state, while in reduction is a process where a substance gains electrons, decrease in oxidation state. Third is the temperature and pressure. These higher temperatures can keep metals dissolved, while cooling causes precipitation. Fourth is the wall rock alteration or the host rock reactivity. This refers to the chemical and mineralogical changes that occur in the host rock surrounding an ore deposit due to the interaction with hydrothermal fluids. Lastly is the boiling and fluid mixing. When hydrothermal fluids boil or mix with cooler groundwater, metals precipitate. Gouge, this refers to the unwanted minerals or rock material that are found alongside valuable ore minerals in a mineral deposit. While the ore minerals contain economically valuable metals or elements, gouged minerals do not have significant economic value and must be separated during processing. As generally used, gouged minerals have no commercial importance in a particular period of time, possibly becoming ore minerals at a later date. They are commonly silicates, carbonates or fluorides, and more rarely sulfides. The gouged minerals of ore deposits formed at high temperatures differ from those deposited at lower temperatures. Paragenesis. This refers to the sequence and relationship of mineral formation in a geological setting, particularly in ore deposits. It describes how minerals crystallize over time under changing temperature, pressure, and chemical conditions. Here are the factors influencing paragenesis. First is the temperature and pressure. This controls which minerals crystallize first. In fluid composition, this determines mineral precipitation and replacement reactions. In structural features, fractures and faults guide mineral deposition. And lastly, in chemical reactions, this is the interactions between minerals and fluid change mineral stability. Sequential deposition. Sequential deposition. This refers to the process by which minerals form in a specific order over time due to the changes in geological and chemical conditions, and it occurs in various mineral deposits, including magmatic, hydrothermal, and sedimentary environments. Here are the stages of sequential deposition. In early stage are the high temperature minerals. In magmatic and hydrothermal systems, high temperatures minerals crystallize first. In main ore forming stage, as temperature and pressure decrease, different ore minerals precipitate from fluids. In late stage are the lower temperatures minerals such as carbonates, clays, and oxides form as the last phase of mineralization. Last stage is a post-deposition alteration. These are minerals here. The minerals may undergo changes due to the weathering, metamorphism, and supergene enrichment. Here are the references of our discussion. Thank you for listening, and we hope that you all learned something.